is equilibrium of a gas system. KSP is called the solubility product constant. And when different ionic solutions are mixed, precipitates often form. If you remember from last year, the percent yield lab, that was a precipitate reaction. We mix two solutions together, we collect the precipitate and filter, we measure the mass of the precipitate, calculate the percent yield, all that. Okay? So, the precipitate often forms. When the precipitate is present in the solution, that is an equilibrium system. You are getting precipitate being formed at the same rate that some of the precipitate is dissolving back into solution. So the presence of the precipitate in solution is an equilibrium system, and as such, we can create an equilibrium law expression to distinguish it from gas systems, because there's certain rules about solutions that are a little bit different. To distinguish it from gas systems, we call it the KSP as opposed to the KE. So it's the solubility product constant, formation of precipitate. Okay? Very quickly, you can read that on your own. It's basically just a review of solutions, terms, terminology, things that you have to be aware of. Okay? Solute, solvent, solution. Heterogeneous versus homogeneous mixtures. Heterogeneous, two or more phases. Okay, so we can see the individual parts of my mixture. Paint, granite. Okay, these are colloidal suspensions. They're called small. Their examples are smog, milk, mayonnaise. Colloidal suspensions versus colloidal dispersions versus colloidal suspensions. With the dispersion, if you leave a glass of milk, hopefully leave it in the fridge, Martin. Don't leave it on the counter.
Don't pull Martin.
Leave it in the fridge and don't touch it for a week.
Oh.
That's why you want it in the fridge. Everybody goes, ew, what, you don't have milk sitting in your fridge for a week?
No. Martin went, I finished it before.
So you go on a Saturday, you buy like 3 bags of milk. On Friday night, what's left? One of those bags of milk. What's that bag of milk been doing? Sitting in the fridge for a week.
So my family goes through milk pretty fast.
Anyway, take a glass of milk, leave it in the fridge for a week, don't touch it, don't disturb it, don't move it, don't do anything to it. Come back and see it in a week, you're going to have a layer of fat floating on the top of the milk.
Oh, okay, that's what
Okay? That would be a colloidal dispersion. Okay, the droplets, even just with the small magnifying glass, doesn't even have to be very powerful, you're able to see globs of fat floating in the milk. If it's left to sit, it settles out of phase. Okay? Mustard, mayo, ketchup don't do that. If you leave that sitting in the fridge and don't touch it for a week and then you go to use it, there's water on top. Right? The water settles out of phase. Okay? Those are colloidal dispersions. Undissolved particles are extremely small and don't settle out of phase. Colloidal suspensions are things like blood. I'm not sure why, but we could ask Martin why he would do it. If you leave blood in the fridge for a week and don't touch it, it's not going to separate into its pieces.
Where did I get this blood?
It'll stay in its dissolved state, and the particles are too small to see with the naked eye, so those would be colloidal suspensions. Homogeneous mixtures, those are our solutions. We only see one phase. It must be transparent if it's in the gas or liquid state. Okay, your solution must be transparent if it's in the gas or liquid state. If it's not, we either have a heterogeneous mixture or one of our dispersions or suspensions. Okay, it must be transparent in the solid or in the gas or liquid state. Example of a gas solution, of course, is air, carbon dioxide, nitrogen, oxygen, all mixed together. We can see through it, don't see the parts. It can be solid, but obviously we can't see through solids. Okay, your metal alloys, brass, bronze, stainless steel, those are all examples of solutions. Okay, we take brass and we make it with iron and copper. We get that copperish color to it, but we don't see the individual parts. So it's all mixed together. Other terms you have to be familiar with, you must be familiar with, unsaturated versus saturated solutions. Okay, if it's unsaturated, it's able to dissolve more solute at a given temperature. But again, be very aware, solubility is temperature dependent. If you're a saturated solution, you have dissolved as much solute as you can at that given temperature. And this is, when we're saturated, this is an equilibrium system. Hint, 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 hint. These are things we're going to do. We're going to try to calculate the mass that we're able to form a saturated solution, or what mass we create. We just don't form a precipitate, or we just do form a precipitate. Those are the kinds of calculations. So, saturated solutions are equilibriums in which the rate of the solute enters the solution equals the rate that the solute precipitates out of solution. Substances tend to dissolve due to the second law of thermodynamics. In other words, for example, if I take my salt crystal, it's going to dissolve because the entropy of that system is going to increase. My sodium chloride is going to dissociate into free-moving ions. I've increased the entropy of the entire system. Okay? Very quickly, take a look at what happens with the different kinds of why things dissolve. Okay, non-electrolytic solutions. Okay, just before we were talking about electrolytic solutions, so these are non-electrolytic. Take a look at polar covalent first. Remember from last year. So basically, what I'm doing is going over the theory from last year, making sure everybody's caught up and up to date with the current theory. A polar covalent solute will dissolve in a polar solvent because of the interaction between the dipoles.
Where's the shake it off?
Remember this phrase from last year. Oh, you better don't make me take out chapter 8 notes and show you where it was. Does everybody remember this phrase?
Like dissolve light. Like
Sorry?
dissolve light. Like dissolve light.
Like dissolve light. No.
That's what Sweetman taught us.
Oh, okay.
Different concept. Why does like dissolve like?
I don't know.
I don't know.
Like dissolves like explains what happens. This explains why it happens.
You have to overcome.
Yeah, I don't remember.
I remember this one. I never understood it. Into my life. Oh wait, is it out? I'm just gonna spend the rest of here, man. The arm on your face. Yo.
Benzene is a very common industrial solvent. It is very important industrial solvent because it is a non-polar solvent. So I don't want that. Hang on. Because we're talking about dipoles now. Hang on. We're going to get back to this one in a minute. I'm changing the rules here. But it's the same basic concept. Okay, so let's say I am
Look at mine. Josh, stop doing
okay. I have a polar solute and I've got a polar solvent. Why do they dissolve? These things are together because there is a certain attraction between solvent and solvent molecules and the attraction between solute and solute molecules. Okay, so we've got. Yes, I just can't stand looking at it.
Yeah.
He pulled too many buttons.
We have a new phrase. He pulled a Martin. Yeah, so that's why he's facing the wrong way.
Wow. And I like the fact that you're on camera there.
Yes, because Daniel and those are in the New York trip.
Oh, shoot, isn't that nice?
Say hi, Miss.
Escape from us.
Hi guys, hope you're having a great time in New York.
We're gonna see this when they come back.
All right. So, We have a certain solute to solute attraction. There's attraction that's holding these solute molecules together. There's an attraction holding the solvent molecules together. If this is going to dissolve, I probably erased that. Thank you. I'll do it again. If this is going to dissolve, then the attraction here has to be greater. So this attraction has to be greater than these attractions. That's why things dissolve. So two polar molecules will be able to interact because of their dipole forces, their positive side and their negative side. That attraction, if it's greater than the attraction that exists already in your solvent and the attraction that exists already in your solute, if this solute to solvent attraction is greater, you're going to be able to dissolve. So the attraction between the negative side of this and the positive side of this, that's the attractive force that allows PCl3 to dissolve into water. Okay, and that's all that this summary here is saying. Okay? Force of attraction between solvent to solute must be greater than the attraction between solute, solute, and solvent, solvent. Results in a negative delta H values and positive delta S values. In other words, dissolving is an exothermic process. Energy is released when things dissolve. And because we're increasing the randomness as something dissolves, that's going to increase our delta S. So we're going to have negative delta H and positive delta S. Large values will be the result of high solubilities. Okay, something can dissolve easily. The larger the delta H and the larger the delta S values, pardon me. Molecules with very low polarity, okay, they have a very low dipole force, they're able to dissolve because water is able to undergo hydrogen bonding. Okay, so this is why water is classified as the universal solvent. Water can dissolve the largest variety of things because it has dipole forces, it has hydrogen bonding forces, and to a certain extent LDF forces. So water exhibits all those, and that's why it has such unique characteristics. Okay? The same thing is talked about when we're looking at nonpolar molecules. Okay, so that's the example I started with. I wanted to start with here. Here are two nonpolar compounds. I've got a nonpolar solute, CCl4. I've got a nonpolar solvent in benzene. There's no dipole forces. How can they dissolve? Just based on London dispersion, LDF. Okay? Even though they're non-polar, they still possess LDF. So therefore, there's a certain attraction with LDF. So it's still this attraction here and here. Those two have to have a stronger attraction than these two or those two combined. Okay, so that still exists. Dissolving between nonpolar solute and nonpolar solvent is due to relatively equal LDF. Therefore, no strong bonds to break, little energy effects to be consumed. So we don't have to worry about delta H, delta S values here, because there's not much energy involved to begin with. They cannot dissolve in polar solvents. The force of attraction is just too great. The dipole force is too great to overcome the solvent. So they're not going to be able to dissolve. Okay, so as I said, all of that's a review from last year. If you want more details on that, check your notes from last year, chapter 8. Okay, and there's pages of detailed explanations of all that. Because I know you all kept your grade 11 chemistry notes.
Yeah, I got those notes last year. So.
Folks, seriously, don't throw out your grade 12 notes if you're taking university chemistry. Okay. If you got your grade 11, keep them as well. Do not throw out any chemistry notes as long as you still have them. Don't throw them out for first year chem. Once you get past first year chem, you can throw them. Go ahead, trust me. All right.
That's why you give it like a funeral party.
Here's a situation that really, if we look at, shouldn't happen. Gases should not be able to dissolve in a liquid. Why? Gases should not be able to dissolve in a liquid. Sorry?
They're less dense, so they don't, like, burn.
You're on the right track, but density is the wrong concept.
Gases.
In order to dissolve, they have to lose energy.
They have high energy.
In order to dissolve, the intermolecular spaces between the gas molecules has to get less. So we literally have to squeeze the gas into the liquid state. So it has to have lower energy, and even more important, considering what we've been talking about, it has to lose entropy. So we can't get the combination of lower energy and lower entropy at the same time. They're opposite forces. So there's nothing that allows gases to, that really theoretically that allows gases to dissolve. Yet gases easily dissolve in liquids. Okay? Even though free gas molecules tend to display greater entropy than dissolved gas molecules, the decrease in energy of the system will favor gases being able to dissolve. They're just going to lose so much energy. Remember that lower potential energy versus higher randomness? The lower potential energy is so great that it does allow gases to dissolve. Now we do have something called Henry's Law. Okay? Henry's Law, partial pressure of the gas, the solubility of the gas is directly proportional to the partial pressure of the gas on the surface of the liquid. In English, what that means is, if we can take that gas and increase the pressure at the surface of the liquid, it's almost like you're squeezing it in. By increasing the pressure, you're increasing the solubility of the gas. You're kind of forcing it into the liquid. Perfect example, 2-liter bottle of pop. Go to the grocery store, pick up a 2-liter bottle of pop that's been sitting there. Do you see any bubbles? No. There's no fizz in a brand new bottle of pop. What does that plastic bottle feel like as well?
Hard.
Rock hard. Okay? You can't squeeze it. Why? It's under pressure. When they bottle pop, the last step is the injection of carbon dioxide gas into the bottle. And they do that under pressure to inject the carbon dioxide and get more carbon dioxide to dissolve. So it has to be done under pressure. You're squeezing the carbon dioxide into the pop. As soon as you break the seal on the bottle, what happens? And then bubbles, and then you can squeeze the bottle. Because as soon as you reduce the pressure by breaking the seal, the pressure is gone, there's nothing to hold the gas in anymore, so the gas escapes and precipitates out. The fizz. It used to be the 2-liter bottles of pop, actually, when they first came out, were made of glass. Couldn't do that because if it was dropped in a certain spot, they literally shattered like hand grenade. There was so much pressure in the bottle. So, boom!
Let's get one now.
They reinforced any glass bottle that does exist now has been reinforced to certain extent.
Oh, it was a Coke one.
So, yes sir.
I want to do that.
No, the gas is actually, there will be some gas because, as I said, sometimes you'll see like gas at the surface, right? But the majority of the gas has been, especially with a fresh bottle, is injected or squeezed into the solution. So it is dissolved in solution. Yeah, and then what happens when you release that pressure, then it all comes out, it literally, that's the term, precipitates out. It's just like the solid coming out. It's the gas coming out of solution, so it precipitates out. Well, yeah, if you shake it. What are we doing when we shake the bottle before we open it?
Yeah, you're not smart.
Dissolving.
You're not smart. You're not smart.
You're pulling
Pulling
over.
my
You're pulling a mark. When you shake the bottle, what you're doing is you're causing some of the gas to come out, but you're increasing the pressure then as well. So you're increasing the internal pressure of the can, and that's why when you open it, more gas comes out. Becomes a big issue with scuba diving as well. Okay, Henry's Law is very applicable to diving. What's inside the tank?
Oxygen.
Air, not oxygen. Air.
Oh, nitrogen.
The problem with oxygen under pressure is actually toxic. Okay, so if you're breathing pure oxygen, under pressure you die. Inside the tank, we have 80% nitrogen gas, 20% oxygen gas, and 0.03% carbon dioxide gas. Okay, now the problem with diving is the tank itself is under pressure. Up to 3,000 pounds per square inch is the average pressure inside the tank. That's why they have that little regulator they have. It's not like it's just a hose that they breathe through. If it was just a hose they breathe through, you'd blow up your lungs like balloons and they burst because all the air would come out under pressure. And you literally go, and you hear it, because your lungs would rupture like a balloon.
And you die.
So what that thing at the end of the hose is called a regulator. What that does is it equalizes or releases the pressure as it's coming in, so it's just you're breathing normal pressure. So the other problem becomes at the surface of the ocean is 1 atmosphere of pressure. Right? Every 33 feet down, the atmospheric pressure doubles. Okay, and you've all felt the effect, even in a 10-foot pool. You go down to the bottom of a pool, what do you notice? Your ears get sore. Right? And that's what that is, your eardrums, my hands can't go that way, your eardrums are bending inwards because of the pressure. Right? So they're starting to go in. Now, as a diver, what you learn to do, and you all done it even on airplanes, the airplane's the opposite effect. The higher you go in the airplane, your eardrums bulge outwards. So what do you do to relieve the pain? You pinch your nose, and you close your mouth and blow. And your eustachian tube connects your throat to your inner ear, your middle ear. And that's why if you'll often have plugged ears if you've got a cold, because that eustachian tube gets full of mucus as well. So there's a small tube from your throat that literally connects your throat to your middle ear, and that equalizes the pressure. So when you hold your mouth and blow, that equalizes the pressure, and the reason you feel the snap is because literally your eardrums are snapping back to position. Okay? So as a diver, what we do as the ears start to bulge inwards because of the increased pressure, you equalize. You do that, and you feel the pop as they snap back into place. So every 33 feet, atmospheric pressure doubles. So 33 feet, you got 2 atmospheres. 66 feet, you're at 4 atmospheres because it doubles. And at 99 feet, which is the bottom of recreation scuba diving without any special equipment, you're now at 8 atmospheres of pressure. Okay? So you're 8 times surface pressure. So you got to equalize all the time, but once you're down there, it's fine. Right? You don't feel it in your body. Your body's used to that, it gets used to that pressure. But the problem is the gases now become an issue because we've increased their partial pressures. So if I increase the partial pressure of a gas and your blood is a liquid, what are we doing? We're increasing the amount of dissolved gas in your blood. Oxygen, not a problem. The cells use it. The cells pick up any extra oxygen and use it for cellular respiration. Carbon dioxide, not an issue. We're going to learn what the body does with excess carbon dioxide in the blood. It's called a buffer system. It's a pH buffer system. You might have talked about it already in biology. So the body's able to handle and get rid of excess carbon dioxide. The problem is the 80% nitrogen. It's an inert gas. The body doesn't use it. It can't absorb it into the cells. So the deeper you go, the more nitrogen is in your blood. Okay? And at 100 feet, you're only allowed to stay down there for about 10 minutes. Okay? So 10 minutes is your maximum time because you get too much nitrogen. It's called getting narked up. Nitrogen narcosis. And it's the same idea as being...
Isn't it a narc song?
It's the same idea as being drunk. Too much nitrogen in your blood, you get the same inhibitions. People have actually taken their tanks off and losing their But anyway, oh yeah, it's really... As you get certified for a deep diver, which I am, they make you feel the experience to know what symptoms to look for. It's just like being really hammered. But here's the problem. So you've been down 100 feet, and you're swimming around, so you got all this 8 times pressure squeezing nitrogen into your blood, you turn a corner and there's Josh. Okay, after you fill your wetsuit, right, and you try to get out of the water as quick as you can. So you swim up as fast as you can. Well, what are you doing? You're exactly like the bottle of pop when you open it for the first time. You're releasing the pressure too fast. All that nitrogen that's been dissolved in your blood comes out just like fizz in a pop bottle. And these tiny bubbles of nitrogen collect in your joints, and when you get to the surface, your capillaries rupture because of the gas in it, and your eyes bleed, your nose bleeds, your ears bleed. It's really cool. But no, it's cool. Because what they do,
Did you stand
I mean, you don't want to do it, but what they do, they rush you back,
Oh, and then you're in like an.
and then they'll throw you in a decompression chamber.
Yeah.
Oh.
And the last question they ask before they throw you in the chamber is, what was the depth of your deepest dive? And you say, I was at 100 feet. So they seal you up to 100 feet, pressure. Well, what happens? All the bubbles dissolve back into your blood. And then they slowly release the pressure, like you're supposed to do, and you naturally breathe out the excess nitrogen in your body.
That one 1,000 ways to die.
Yeah, someone messed up.
Like the old
Diving's safe. I've seen sharks and everything.